In the last video, I covered the algorithm that finds the median of two sorted arrays. What if we want to generalize this to finding the kth smallest element of these two arrays? So this is what we are going to do in this video. I say the kth rank element of n ordered elements is the element that is larger than exactly k minus 1 elements in the set. This is just another way to define the kth smallest element. In this problem, we are given two sorted arrays A of size n and B of size m, and the goal is to find the kth rank elements in A and B. The goal is to have the running term in the order of log n plus log n. So how do we approach this problem? We look at the two middle entry, n over 2 and m over 2 of A and B respectively. Now, if k is larger than or equal to n over 2 plus m over 2, then we divide it into two subcases. If a of n over 2 is larger than or equal to b of m over 2, then I claim that roughly the left half of b of 1 to m over 2 minus 1, have rank less than k. This is because these elements are smaller than half of b and half of a. Okay. Therefore, if you do the calculation, their rank is at most k minus 1. So you can feel free to pause the video and check the calculation. Now, what do you do with this information? So you know that your target is not in the left half of B, which is B1 up to Bm over 2 minus 1, because these elements have ranks less than k. Therefore, you can throw away these elements, so you only look at B of m over 2 up to m and A of 1 to n. But because you throw away some of the elements that are smaller than the target, now you have to adjust the rank. Because you throw away m over 2 minus 1 elements that are smaller than the target, so you want to recursively find the k minus m over 2 plus 1 rank element in B of m over 2 to Bm and A of 1 to n. The case that A of n over 2 is smaller than B of m over 2 is analogous. Instead of throwing away the left half of B, you throw away the left half of A. Alright, so let's look at the second case. If k is strictly smaller than n over 2 plus m over 2, again, we consider two subcases. If A of n over 2 is larger than B of m over 2, then the elements in the right half of A will have rank strictly larger than k. This is because they are larger than half of the elements in A and half of the elements in B. And you know that n over 2 plus m over 2 is larger than k. So if you check the calculation carefully, the elements in A n over 2 plus 1 up to A n will have rank larger than k. So what do you do with this information? you can throw away basically the right half of A, and you recursively find the kth rank element in A1 up to A n over 2 and B1 up to Bm. The second subcase is analogous, where an over 2 is smaller than bm over 2. You can check that you can throw away the right half of b instead. Alright, so when n is smaller than 1 or m is smaller than 1, we have the base case. Here you can solve the problem in constant time, and I will leave it as an exercise. Shouldn't be too difficult. How about the running time? In each recursion level, we shrink one of the two arrays size by a factor of 1/2, and we can shrink the size of A at most log n time and the size of B at most log n times. So there should be at most log n plus log n level of recursion. At each recursion level, we only do a constant amount of non-recursive work. Therefore, the running time is log n plus log n. That completes the explanation for this algorithm. I hope you find it helpful, and then I will see you again in later other videos. Thank you for tuning in.